We are at chapter 3, elementary fluid dynamics, the Bernoulli equation. We are going to finish this chapter today. We will begin today with static, stagnation, dynamic and total pressure. We know there are three parts for Bernoulli's equation. We have raw energy or raw pressure of the fluid, then we have potential energy per unit volume, and then we have kinetic energy per unit volume. So if you look at this equation, it has a unit of pressure. I'm going to dissect this equation in a different way. So here for the first part I'm going to call it as a static pressure. For the second part I'm going to call it as a hydrostatic pressure. Third part I'm going to call it a dynamic pressure, and then collectively whatever I'll get the sum I'm going to call it total pressure, which will always stay constant throughout the flow. Now if you are designing horizontal machine, let's say steam turbine, in that case the inlet and outlet of steam turbine is at same height, and then therefore H1 and H2 is same. I can neglect these hydrostatic pressure. In that case I have only two pressures to deal with. One is known as static pressure and then dynamic pressure. So collectively the sum of these two pressure is known as stagnation pressure. It's a pressure at stagnation point where the fluid particle comes completely at the rest and it transfers its energy to the solid, to the, let's say, blade of a turbine, and that's your stagnation pressure. If you are designing steam turbine, the stagnation pressure plays very important role. So this is a sum of static pressure and dynamic pressure. This is also used in Pitot tube or Pitot static tube. If you have if you are waiting on airport and then if you are looking at the plane, you will see these kind of Pitot tubes attached to the plane. These are nothing but Pitot static tube, and then where we can measure local velocity. This is your stagnation point here, and then based on this brief pressure difference between static pressure and stagnation pressure, which is total pressure of the fluid, you can find out, we can use Bernoulli's equation, and then you can find out total velocity. Let's see how we can do that in the problem later. Now Pitot tube was invented by the guy named Henry Pitot in 1732. It is used to measure airspeed of an aircraft, water speed of a boat, and to measure liquid and air gas velocities in industrial application. One of the important thing about Pitot tube is always measure local velocity at that point. So many times you will see that there are multiple Pitot tubes attached to a plane, or if you have large pipe, then there are 2, 3, 4 different Pitot tubes in the plane, in that pipe. Let's do a problem for Pitot static tube, and let's see how does it uses Bernoulli's equation to get local velocity. So as I said before, stagnation pressure is sum of static pressure and dynamic pressure, and in case of Pitot tube we are going to neglect hydrostatic pressure because the air density is very low. So we have our Bernoulli's equation here: static pressure plus dynamic pressure is equal to total pressure. So this is my PS static pressure. Total dynamic pressure is the density velocity squared by 2. That's my dynamic pressure, total pressure here. My objective here in this problem is calculate velocity. Here flow is horizontal and lots of air is going through this Pitot tube. And then this is a white part, that's your head-on total pressure or stagnation pressure is measured here. And then your static pressure is measured in this yellow part. Now if you look at the equation, and if I can rearrange the equation for velocity, I will get velocity square equal to, actually I have to calculate, equal to 2 into total pressure or stagnation pressure minus static pressure divided by density. And that's the equation I will get for the Pitot tube. So all I need to know is the difference between my stagnation pressure and my static pressure. So here we have a diaphragm on this Pitot tube. It calculates that difference, and that difference is given to a computer, and then computer can calculate velocity. So basically computer runs with this Bernoulli equation. So here I have difference. Once you have difference, you should be able to calculate velocity. So static pressure in this case is 101,000 Pascal. Total pressure, which is stagnation pressure, in this case is 105,000 Pascal. So it is given in kilopascal. You have to convert that into pascals, and if you do that conversion, put the numbers in, you can calculate how much is the velocity. So if you want right now, you can pause the video and then you can calculate the velocity. So static pressure here 101,000, total pressure 105,000. The difference will be 4,000 Pascal. If you put that 4,000 here, the velocity will get is around 80.8 meter per second. So if you are using this Pitot tube for high velocity, you can measure that velocity just by knowing the difference between stagnation pressure and static pressure, and then you can use Bernoulli's equation and calculate velocity, which in this case is 80.8 meter per second, and that's how Pitot tube work. So that's the application of Bernoulli's equation for Pitot tube. Now we will move on for the application of Bernoulli's equation for process of siphon. We all know what siphon is. Now siphon is basically a tube. Let's say we have a vessel here at high elevation, and then another vessel at low elevation, and then you have some water filled with water inside your one vessel, and then you have a tube filled with water and then goes to lower vessel. In that case, the water is sucked because of the low pressure inside the tube, and then it's transferred to the vessel at lower level. So here what's going to happen is that we have relatively high pressure here, which is atmospheric pressure pushing on this liquid, and low pressure is created in this part or here. Because of that low pressure, water always goes from high pressure to low pressure. High pressure here, low pressure here, water is going to get sucked and is going to get transferred into this lower level. And that's the application of Bernoulli's equation in siphon that what we are going to do. So here we have a problem. This one is a solved problem from the book. What's happening in this problem? A liquid can be siphoned from the container. So we have this container here, or large tank, let's say. It's a 4.5 meters in height. And then here we have a tube going through at this point here. And then what we have to do is calculate maximum possible height, in this case without cavitation. So what's happening here? And when the water flows from this point to this point to this point, the low pressure created here, and because of that, high pressure here, low pressure here, water is going to go upward and then it's going to go downward at point 3, and then we are going to get this action or process of siphon. Now what happens is that we have a limit for this height. It's not like we have infinite, we can go for this height infinitely, even though these 2 points at the same level. This one is slightly higher, this one is slightly lower, and then we have limitations for this height. What's going to happen is that as low pressure created here and water is going to get sucked, there will be a time where that pressure will be so low that at certain moment the water will begin to boil, and that's pressure what we call as vapor pressure, and the process of that boiling water is known as cavitation. Cavitation is nothing but formation of vapor bubble or vapor cavities or steam cavities. So what's going to happen here? As soon as you start increase the height, the pressure here is going to decrease, and there will be certain point. Now water, it says, is at 15 degrees Celsius. So as at 15 degrees Celsius, the water vapor pressure is 1710 pascals or 1.7 kilopascals. So if the pressure goes below 1.7 kilopascal at this point, water will boil, and then you will have formation of cavities or formation of steam bubble, and then as steam density is different than water, water will not flow through this pipe. So you have a limitation for this height. Up to certain limit, up to this pressure, you can go for the height. Beyond that you cannot do. So what we have to do in this problem is that determine the maximum height h over which the water can be siphoned without cavitation, and that's the whole idea, without cavitation, without formation of steam bubbles. That's what we have to do. We have to find out maximum possible height. Now for this problem there are two ways to solve the problem. The first one is that we can start with point 2 and point 3, and then we can run our Bernoulli's equation there, and then you can calculate height. Or there is a second way, something that they did in the book. We can start with point 1 and point 2, and then point 1 and point 3. We have two equations, two unknowns, and then we can solve it. We are going to solve it with both ways or both methods. So first we start with method number 1, direct approach. That's your Bernoulli's equation between point 2 and 3. So we have point 2 here, we have point 3 here, and we are going to apply our Bernoulli's equation point 2 and point 3 to calculate this height. So here is my Bernoulli's equation, P2 1/2 rho V2 square plus rho G Z2, and then we have point 3 is the same thing. We have pressure energy, we have dynamic pressure, and then we have static pressure or hydrostatic pressure. So we have these three, we have this equation from point 2 to point 3, and then we all know that we can see that the diameter of the pipe is not changing. What does it mean? That is the area of cross section is same, and if area of cross section is same, it means that I can apply my continuity equation. Continuity equation says that A2 V2 is equal to A3 V3. It means that as area is same, V1 is going to be equal to V3. So as V1 is equal to V3, I can cancel these things out. I can cancel V2, I can cancel V3, and then that's what I'm going to do, and then I'm controlling my equation. So that's what I do now. I cancel my V2, I cancel my V3, and now I have 4 terms. I have P2, I have rho G Z2, I have P3 and rho G Z3. Now I'm going to work with my equation. So my objective is to, when the pressure is this one, 1710 PA, at this point I want to know height, because after that if I raise, pressure will go down, let's say 1700, 1600, 1500, steam bubble will form and then water will not flow. So the maximum possible height 1710 PA I can reach, and I can still water can continue to flow. So my P2 here will become 17.10 PA. So that's the number I'm going to put there, 1710 PA, if you can see that. And then here the point 2, elevation point 2 is Z2 here. So that's my Z2 H. I have to calculate, so I'm going to put question mark there. Density and gravity is going to stay constant. I have to calculate that, keep that in mind. P3, here is we have free jet, and any time you have free jet, you have atmospheric pressure. So here P3 is nothing but atmospheric pressure, which is 101,300 Pascal or 101.3 kilopascal. And then finally I will have this rho G Z3. Now you need to know the important thing about this Z3 is that we have our datum here at base level of water tank. So our Z3, anything below datum, you need to take negative. So we have negative sign for Z3. You can do this problem in another way, where you can take, if you want, you can take your datum at 0.3 and then you will get height from the datum, entire height from the datum in this problem. But in this, they have asked us to calculate height from the base of the tank, and the datum is the set there, so we are going to do the same. But 0.3 is below the water tank, below the base level of water tank. So I'm going to take that minus 1.5. Remember, this minus is very important. If you forget that minus, you are going to get wrong answer. So make sure that you understand that you have negative sign here. And now if you want, you can take some time, you can pause it, and then you can run your numbers. Pause the video, run the numbers, put the pressure 2 is 1710 Pascal, height keep it like that, you have to calculate. Pressure 3, put atmospheric pressure 101,3000 Pascal, and then this one is negative 1.5 height, density, gravity. And if you run the numbers, if you pause the video, you will get your right answer. So here I'm going to do this calculation quickly for you, and then if you do this calculation, you will get final answer as 8.65 meters per second. It means that this height comes around 8.65 meter altogether from the datum, or about 4 meters from the water level here, and that's the height that you can get. If you go beyond 8.65, if you go 8.7, 8.8, 9 meters, then what's going to happen, in higher you go, this pressure is going to decrease. 1710 will go to 1650, 1600, 1500, vapor bubbles will form, water will stop flowing. So that's the maximum height that you are going to get, 8.65 meters, by using the Bernoulli's equation from point 2 and point 3. And that's how you solve the problem. It's a simple problem, application for Bernoulli's equation for the process of siphon. The reason it works is that we have same energy at any given point, at point 1, point 2, point 3. So you can use that relationship between point 2 and point 3 and calculate this height. Now there is another approach that we can use here. Another approach is that in this, what you can do is something that they did it in a book. You can start with equation between point 1 and point 2 first, and then you will get an equation with 2 unknowns. Then you can date another equation between point 1 and point 3, and then you have another equation, and then you can solve this equation simultaneously, and then you should be able to get the height. So that's another approach. So the second approach says that Bernoulli's equation between point 1 and point 2, you apply your equation. Now pressure here is 1 atmospheric pressure. Here we have pressure 1 atmospheric for between point 1 and point 2. velocity, this water level is going down at very slow rate. We are going to assume the tank is very large. So as well, I'm going to neglect that velocity. Velocity is 0 meter per second. Then here the height for the water level is 4.5 meters. So I'm going to put that 4.5 meter for the height. Vapor pressure, P2 is vapor pressure is going to be 1710 kPa, 1710 PA, 1710 pascals. And then we don't know V2 in this case. V2 is velocity at this point. We don't know that. We are going to keep it like that. And then we have to find out H, which is height, which is they have asked us. So you can see here we have one equation and two unknowns. We don't know V2, we don't know H. So what we are going to do is that we are going to take another equation. Now for that, the equation will be between 0.1 and 0.3. So here in 0.1 and 0.3 again I have pressure 1 at 1 atmospheric pressure. So at this point 1 I have 1 atmospheric pressure, and then 0.3 is a free jet. Again here we have 1 atmospheric pressure. So I'm going to cancel that 1 atmospheric pressure. I'm cancel P1, cancel P3 here. Then we are going to work with our continuity equation. In continuity equation we know that V2 is equal to V3. So this one is nothing but V2, and then once I can find out value of V2, V3 I can put it for this in this equation I can find out if I have V2 I should be able to find out height. So my V3 is nothing but V2. V1 velocity is 0 meter per second is the same thing. The height is Z1 is the same. Height Z1 is 4.5 meters is going to stay same. So I'm going to run my equation. Here Z3 height I'm going to put it again minus 1.5. This is my Z3 height, so that's my minus 1.5. I'm going to put that minus 1.5 there, and then I'm going to run my equation. Once you run this equation, you can pause the video if you want, and you can run your equation. Once you run your equation, you will get this V2. Once you have V2, you can put that V2 or V3. It's the same thing. You can put that in this equation number 1, and then you should be able to calculate height, and that's your final objective. So if you do your calculations, what you're going to get is V3 or V2 is going to be 10.85 meter per second. It means the water is coming out from this side is 10.85 meter per second. It means that velocity V2 is also 10.85 meter per second. So you can use that velocity V2 10.85 here in this equation, Bernoulli's equation between 0.1 and 2, and then you should be able to calculate height, which is what they have asked. So your height, and if you can pause the video, you can run the equation, you will get same answer. That's what we got with previous method, which is around 8.65 meters. So your height will still be 8.65 meter per meter. That's going to be your maximum height. So either way, it doesn't matter from how you do it, from 1 to 2 or from 2 to 3, 1 to 3. Either way, you can work your way with your equations, and then you can find out the final height, which is 8.65. And that's your application for Bernoulli's equation to Siphon problem. Now we are going to move to the next part. For flow rate measurement. If you visit industry, let's say any industry, a power plant or a chemical plant, any plant you visit, the most important thing or most notable thing that you will see in the plant is lots of pipes. So many pipes you are going to see in that plant. And these pipes carry lots of fluids, lots of liquids and gases. And these are important liquids and gases going through pipe. And if you want to have an efficient operation of that plant, you need to make sure that you know how much flow is exactly at any given time, exactly flowing through this pipe. You need to know that number of flow rate to run an efficient operation. And for that, you need to design a device which will measure that flow rate. You have to have device installed in these pipes so that you will have exact number for the flow rate. These flow rate measurement devices are based on Bernoulli's equation, and some of these devices we are going to see today. So these devices are normally known as orifice meter, nozzle meter, venturi meter, and Pitot tube. That's what we have seen based on stagnation pressure. So now we will see other three devices: orifice meter, nozzle meter, and venturi meter. Now these devices work basically on something known as a differential pressure flow measurement principle. what does it mean, differential pressure? It simply means that they measure pressure difference between 2 points. So let's say, for example, we have this orifice meter. Now orifice meter, and we'll go through that shortly. Orifice meter is just a plate with a hole in it, and then we have high pressure here and low pressure at this point. Because of the, as your fluid goes through narrow section, velocity increases, pressure decreases, and you measure that pressure difference, and you should be able to calculate flow rate. And that's what even nozzle meter is, that's what venturi meter is. So what is the concept, what is the formula that they use? So we know we have a Bernoulli's equation here, 0.1 and 0.2. So 0.1 here, for the first part we have 0.1 here, let's say we have high pressure here, and then we are going to have low pressure here. Because of the obstruction, again same thing, we have obstruction, we have high pressure here, we have low pressure here. Because of this narrow section, we have high pressure here, we have low pressure here. So we have 0.1 here and 0.2 here, and that's my 0.1 with high pressure, and then here my 0.2 with low pressure. Now we have another equation. What we are going to do in this part is that as they are horizontal, we are going to cancel these two things here. We are going to cancel this rho g h1, and then we are going to cancel this rho g h2. And if you cancel these h1 and h2 as they are horizontal, we have only 4 terms to deal with. Now you can deal with these 4 terms. Take this out. So we have these 4 terms here, and then I'm going to apply my continuity equation. Continuity equation says Q, my flow rate, is equal to A1V1 is equal to A2V2. So my area A1 is here, this is my A1, this is my A2, and then whatever the velocity is, I'm going to have high velocity here, I'm going to have low velocity here, and then altogether flow rate at this point and at this point is going to stay same. So if you look at it here, I have V1 here, I have V1 here, I have V2 here, I have V2 here. I can use these both equations if I play around long enough with these both equations. First one is my Bernoulli's equation and another one is my continuity equation. Then I will get a final equation for a flow rate, and that equation will look something like this. Q is my flow rate is equal to A2 under root 2 P1 minus P2 by rho 1 minus A2 by A1 square. So that's the equation you get if you play around with these two equations. You will get final equations like this to flow rate measurement. It means that with this equation I can measure a flow rate through these devices, whether it's orifice meter, nozzle meter, or venturi meter. If you look at this equation here, A2, it's constant. Area here, here, here is constant. Density of the fluid is constant, and then A2 by A1, that's the ratio, is also constant. So only thing that could change is P1 minus P2, that's your pressure difference, the difference between here and here. So if you want, you can attach manometer and can find out what is the pressure difference. So if you have a computer, all that computer needs is this pressure difference, the reading from P1 and P2, and then computer can use those numbers from P1 and P2 and then tell you what is the flow rate, how much amount of flow is going, and that's what the computer, or that's what these devices do. They simply measure pressure difference, and once you have pressure difference, you can calculate flow rate, and that's your flow rate measurement by using Bernoulli's equation and continuity equation. And that's how this thing works. So now we will go through one by one these pressure measurement devices, and they are called as differential pressure flow meters. So first device that is differential pressure flow meter, differential flow meter is this orifice meter. Orifice meter is one of the simplest and cheapest device. In this device what we have is this kind of orifice plate. So we have a pipe in which I'm going to put this plate in here. So as my flow comes from this side to this side, velocity is going to increase, pressure is going to decrease. So I'm going to get high pressure here and low pressure here. And because of that pressure difference, I'm going to take that pressure difference here, P1 minus P2, and then I should be able to calculate flow rate. So it's very simple idea to calculate flow rate. So that's my orifice meter, is simplest and cheapest device to measure pressure difference and then calculate flow rate. Another device I have is this nozzle meter. Now in this nozzle meter, what I have is a nozzle, something look like this, here or here. The idea is same. Instead of orifice plate, I have a nozzle. So high pressure here, low pressure. As soon as the water comes out of this nozzle, you can imagine velocity will increase, low pressure will create it, so low pressure here. You can measure that pressure difference, you can put it here again, P1 minus P2, and you should be able to get flow rate. And that's the general idea for the nozzle meter. This is slightly expensive than your orifice meter. And then I have Venturi meter. It's slightly more expensive than orifice and nozzle meter, but it's very accurate device to measure flow. Now in reality it will look something like this here. So we have a converging diverging nozzle here. We have, let's say, a nozzle and a diffuser section here, let's say. And then as soon as water enters to this next section, the lowest pressure is formed here. So low pressure here. Before entering high pressure here, you can measure that pressure difference here and then put that pressure difference here, and then you should be able to measure flow rate. And that's the simple idea of this Venturi meter. So altogether, whether it's orifice meter, nozzle meter, Venturi meter, the idea is simple. They have some kind of obstruction, because of that you create this pressure difference, high and low pressure, put that pressure difference here and then calculate flow rate, and that's how these devices work. Now let's do a problem. In this problem we are going to use Venturi meter. For this problem what we have is the Venturi meter is used here, and then what we have is the diameter for the Venturi meter, inlet diameter for the Venturi is 0.1 meter, and then the neck diameter for the Venturi meter is 0.06 meter. So we are going to get high pressure here, we are going to have low pressure here, and then because of that pressure difference, there you can calculate flow rate by using your Bernoulli's equation. So in this problem, what we have to do is to calculate range for pressure difference. So here what they have said is that for this problem is the flow rate is given, the range for the flow rate is given. The first part of the flow rate is 0.005 meter cube per second, and then final part of the flow rate is 0.050 meter cube per second. So that's the Q is already given. So if we have this equation, the Q is already given, and then it says that determine the range in pressure difference P2 minus P1 needed to measure these flow rates. And that's the idea, that we have to find out P2 minus P1 minus P2 range for P1 minus P2. It means that we are going to get two numbers here, or two answers for P1 minus P2. First one, P1 minus P2 for here, and then for this one, P1 minus P2 we have to calculate, and that will be your range. So for the first part, what we are going to do is we are going to rearrange this equation. For P1 minus P2 it will look something like this, and then for the first part we are going to take this 0.005 meter per second here, and then we are going to calculate P1 minus P2. That will be my first part for the range, and then for the second part I'm going to take the 0.05 here, and then still going to calculate P1 minus P2, and then I will get that the range in pressure difference needed to measure these flow rates. So here you can pause the video, you can do your calculations. Here this is a solved problem from the book, so I did my calculations already. I have P1 minus P2 for the first part. When I will use this flow rate 0.005, I use that, I run my numbers, and then I'll get the number 1.16 kilopascal. So that's my first part, 1.16 kilopascal. And then second part I'm going to use this number here, and then I can calculate P1 minus P2, and if I do that, I'll get another answer is around 1.116, and that's my range, 1.16 to 116 kilopascal P1 minus P2. It's a very simple problem. All you have to do is find out P1 minus P2, the range. So you have already flow rate, you have already equation, put it in the equation, you can run your numbers and calculate this range. It's again very simple problem. So that's the problem for Venturi meter. Now we will learn something about energy line and hydraulic gradient line. We have a Bernoulli's equation. This is a mathematical form of Bernoulli's equation, but there is another way to look at this equation. Sometimes it is useful. It's called a graphical form of Bernoulli's equation, and that's what we can do with this energy line and hydraulic grade line. We can see the equation in graphical form, and that's the idea. But to see it in graphical form, we have to modify this equation slightly. So here in this equation, I have pressure, I have density, gravity, height, I have 1/2 rho v square. What I'm going to do is that I'm going to divide this equation with density and gravity. So if you remember from the chapter 1, density and gravity is nothing but specific weight given by letter gamma. So this is my letter gamma, is nothing but density and gravity. That's my weight per unit volume. What I'm going to do now, to get my equation, or to get that graphical form for the equation, I'm going to divide this equation with this gamma or rho g, and if I do that, this will become p by gamma or p by rho g. This will rho g cancel, this will become just h, and then this one will become 1/2 v square by g. Let's do that. Let's divide this equation by rho g. If I do that, I will get another form of Bernoulli's equation. Here, as I said, p by gamma, p by rho g, v square by 2g, and then z. So this height, instead of height, I'm going to call it z. That's my elevation. And then this one is again same thing. Again, these both equations are same. This one and this one. Only difference is that we have divided this equation right hand side and left hand side with rho g. Now initially, this equation has a unit of pressure. So here unit is PA. Then for this one, once you divide it, it has unit of length. So length is in meters. That's my unit in meters or feet. Now in some books, or in this book or in other books, you will probably find this form for Bernoulli's equation. So don't freak out, it's just still same thing. This is your Bernoulli's equation with unit for the pressure. This is the unit, your Bernoulli's equation with unit for the length or in meters. So that's your equation, p by gamma, v square by 2g, z, and then whatever the constant along it, I'm going to call it as a head. So here for this equation, I'm going to say this one, this term as pressure head. This p by rho g, that's head due to pressure. This one I'm going to call it as velocity head, that's head by due to velocity, and this one I'm going to call it as elevation head due to its elevation, and collectively whatever the head is going to, I'm going to call it as total head. So total head always remains constant, and that's going to be my form that I'm going to use for Bernoulli's equation to understand this graphical form. So again, this one equation is the same equation. So if you come across this kind of equation, p by gamma v square by 2g plus z is the same Bernoulli's equation. So let's see what is this energy line and what is this hydraulic gradient line or hydraulic grade line. So let's assume that I have a large tank here, and then water is going to flow through this pipe here and then again through this pipe here. So I know that this is my Bernoulli's equation in different form. I know that my water, my energy level at any given point is going to stay constant. So this head, that my total head is always going to stay constant. So what I'm going to do is that from this line, I'm going to draw a line and I'm going to call it energy line or EL. So here, whatever happens, this EL is nothing but my H or total head is always going to stay constant. And then I'm going to draw another line. As velocity decreases or velocity head decreases, I'm going to draw another line. As velocity head increases, the rest two heads decreases. So for the decrease, I'm going to draw another line like this one here I have, and I'm going to call it hydraulic grade line or HGL. So what's happening here? Initially, you start with this point, you have high energy, and then your energy, total energy of the system is going to stay same. That's your energy line. But then, as water enters through this part, velocity will increase, and as velocity will increase, the other two heads, your pressure head and elevation head, will decrease. So here I'm going to go in decreased form, and then at this point again velocity further increases, so velocity increases further, so I'm going to get decrease in hydraulic grade line, and then I'm going to continue with this grade line. So here, what is hydraulic grade line? Is the sum of pressure head and elevation head. So sum of pressure head and elevation head. I'm going to put that here. And then, so if I have these two lines, that's the energy line and hydraulic grade line, I don't have the entire geometry, and then I have these two lines. In that case, I can actually see overall what's happening. I don't need to know geometry. Based on these two lines, I can see overall how the water is flowing, what's happening with the entire water, and that's your graphical form to understand Bernoulli's equation. All you need is these two lines to understand that, and that's how these lines work. Let's say we have another geometry for here, to understand energy line and hydraulic grade line. Now in this geometry, what we have is a pipe which is narrowing in cross section area, and it's going upward direction. So energy line at this point will stay constant, and then hydraulic grade line will decrease. So as the water goes up, here as area of cross section changes, velocity increases. As velocity increases, velocity head will increase, and then the other two heads will go down, and that's what we can see here. The sum of pressure head and sum of elevation head is going down here, and then that's how you can draw it, your hydraulic grade line, and that's how you can see it. So that's your graphical form for Bernoulli's equation: energy line, which will always constant, and hydraulic grade line. As velocity increases, the grade line decreases. So that's the part with the graphical form, and now we will go with the final part, the restrictions and limitations for Bernoulli's equation. We know our Bernoulli's equation. We made some assumption for Bernoulli's equation. So this is our perfect form of Bernoulli's equation. At any given point is going to stay same. But life is not so perfect. So every time their conditions will not be perfect, and then when the conditions are not perfect, we may have to modify this original form of Bernoulli's equation. So we will see today for this final part limitations and restrictions for this Bernoulli's equation. The first limitation is viscous effect. As viscosity of the fluid increases or the surface roughness is high, you are going to lose energy, and as you are going to lose energy, you are not going to get this constant at any given time. So if viscous effects are more, then there is a room for error, and that's the limitation for Bernoulli's equation, that you have to modify the Bernoulli's equation, and we are going to modify that in chapter 8 later, but you don't have to worry it right now. That's your first limitation. Viscous effect are important so as non-conservative or energy losses occur. It means that if the friction is more, you are going to lose energy due to friction, and that's your non-conservative loss. Then unsteady effect. Unsteady effect means if there is a flow flowing and then it's accelerating or decelerating with time, that's called unsteady effect. And then you have to modify your Bernoulli's equation. So for the first part, initially at inlet is going to stay same, and later if flow is accelerating or decelerating, you have to add one more term. This dv by dt is your acceleration from point 1 to point 2. You have to add that term, and then you have to write down your equation. So that's your unsteady effects. You have to modify the equation. Initially we assume that this equation will work under steady conditions. It means the acceleration is 0, it's constant velocity. But if velocity is not constant for some reason, then you may have to deal with this unsteady effects. Then compressibility effects. We assume that this equation works for incompressible flow. But if you are having gases with under large pressure, they are going to compact, they are going to contract, they are going to expand, they are going to get compressed. And if that happens, then there is a considerable room for errors for gases. So that's the compressibility effect. You have to again modify equation for gases which can be compressible. So that's a compressible effect, that's a limitation. And the final limitation is rotational effects. Rotational effects means, let's assume that there is a turbulence in a flow, or there are eddies formation or rotational current formation in the flow. If that happens, you are going to lose energy, and therefore you have to modify again that equation. Rotational effects use Bernoulli's equation to restrict flow along the streamline. So we assume that flow is streamlined, there are no rotational effects, but in reality there is always a whole lot of turbulence, because of which you are going to lose energy, and you are going to need to modify this equation. So these are the limitations: viscous effects, unsteady effects, compressible effects, and rotational effects. these are the limitations for this original form of Bernoulli's equation, and in the future we are going to make some of this modification to understand Bernoulli's equation. For now, for this chapter, you don't have to worry about it. You should have to concentrate on this form of Bernoulli's equation, and these are restrictions and limitations for Bernoulli's equation, and that's your chapter 3. Now this one is a practice problem, it's not a homework, it will be there on the blackboard, you can solve it, and that's pretty much it, chapter 3. Alright, well, that's all for today. Stay safe, and I will see you with chapter 7. Thank you.